So this is lecture 8 of our compiler design module. We're going to talk about exceptions and the implementation of object-oriented languages, actually just a few of the features. I tried very hard to find a way to explain these implementations for C++ based on how GCC translates into assembly language. Well, it's too complicated to fit in a 2-hour lecture. Well, if I will ever find a way, I will create a lecture and I will put it up there, and I will create a recording, and you will be welcome to view it. But for the time being, unfortunately, we'll have to resort to going through last year's material on the same subject. So we will showcase the implementation of exceptions and object-oriented languages as a translation from C++ into C. This translation showcases the principles very well, so hopefully you will be able to see how this would work at the level of generating assembly language code. All right, so let's start. So this is the outline for today. We're going to look at exceptions, and we're going to look at a few features of object-oriented languages. For exceptions, we're going to look at two types of implementations, checked and unchecked. So this is the Java type of implementation. And actually, I verified this because if you look at the Java native interface, right, at how to mix C code with Java, when you put a piece of code, so the code that you write in C, right, can be called from Java and then further call some other Java methods, right? And it returns. And when it returns, it has to potentially pass on exceptions that are issued, that are generated inside this Java nested call, right? So imagine that there's an exception thrown here. This code has to pass on the exception to the upper module right here, which might have a handler for the exception. So this is how checked exceptions are implemented. My inspiration for this implementation was the way it is done in Java. There is also a old C++, so this is old C++, way of dealing with exceptions, which is similar to unchecked exceptions in Java. So this is again verified by the Java native interface modules. So that's where I was inspired of using it. It uses the functions set, jump, and long jump. The current implementation of the current GCC uses an implementation for C++ that is somewhere in between. It's not quite checked, not quite unchecked. What's the difference, main difference in between checked and unchecked? So I'm using the Java terminology here. Checked exceptions must be declared if they're not caught. So you have a function or a method m, right? With some type t here and some arguments. And you inside here, I'm just going to write it like this. So open brace, inside here we have some method m1, and this method m1 might throw an exception. Inside m1, inside the call to m1, an exception might be thrown, right? So you have two possibilities, right? Either you provide a try catch here, so this is our checked exceptions, right? Either this, or you have to declare it here. Okay, so this would be checked, and this is in principle not very modular, because you would like to use library methods, right, from your top-level program. You would like to use library methods, and maybe this library method takes a pointer to M1 here, or the address of M1 here, right? and calls M1, and M should not be aware of the fact that an exception is thrown. So checked exceptions are a bit unmodular for that reason, but the Java people, if you listen to them, will have a their own reasons to argue that checked exceptions should exist and which kind of methods should throw checked exceptions and which shouldn't. So we have the checked exceptions. We'll see the implementation for that. We also have the unchecked exceptions. The unchecked exceptions, which are in general errors in Java. So they are subclasses of error. All right, they don't need to be declared even if they're not caught. So this is a lot more modular because now if you take the address of M1 and put it here as an argument and call M1, and M1 throws an exception, this M does not need to be aware of that. Right? The exception would pass through M, would be generated inside M1, would pass through M without M having to be aware of that. And we're going to verify in our implementation of unchecked exceptions, we're going to verify that this is possible, right? We're going to have a situation where F calls G, which calls H, and H throws an exception, and then, so this is G, and then F catches the exception, and then G doesn't want to be aware of the fact that an exception is ever passed through, right? And the implementation will allow that. For object-oriented languages, we look at two important features. We're not looking at encapsulation because that is essentially a typing issue, right? It's a semantic issue. You can enforce it through types. You add modifiers to the types of the class members in the form of public, protected, and private, and then those are enforced. However, things that require an implementation, right, code to be generated in a certain way, are these features: polymorphism and inheritance. They need a certain approach, right? A certain manipulation of pointers to functions, as we will see, that allow these properties to exist. And we're going to try to explain. So let's start with exceptions, and these are a few general facts. They're very useful for error handling. Most often, the place where the exception is generated, right, the place where an exceptional condition is encountered, for instance, division by 0, is not the best place to handle that error, to correct that error, right? So let me give you an example. Let's say you want to open a file. And we're in the old times where the file may reside on a removable media, on a diskette or a CD-ROM or something like that, right? So you press the button to open, and you type in to open. You're in a windowed application, in a GUI application, in a graphics user interface. You open a button, you press a button, a menu opens. You try to access the drive is not there. So there will be many levels of calls between the button press, right? And so there will be many calls to the function that actually accesses the media, right? So in general, this is where the error is observed. You call a system function, it returns a error code, right? And you handle that error code. The problem is that there's nothing you can do right there. What you need to do is come back to this level, all right, and then open maybe a modal window, right, where you say, well, you give the option to the user to either cancel or retry, right? So this would be the right place to do it. The error is generated very deep in the hierarchy of nested calls, but it needs to be handled at the very top level. Now, before exceptions came around as a concept, what people used to do was to return an error code, right, through the entire hierarchy, right, one level up until you reach this level, and at this level, that error code can be handled, can be something can be done about it. But this is very tedious because if you have a function, for instance, that returns an integer, now you have the problem of encoding an error code inside the result, right? And sometimes it's easy because, let's say, your integer result is always positive, so you can use negative numbers to return an error code. But it's not always that easy. right? And why should this function in the middle, which may come from a library, right? So this function in the middle you might not have control over it to change it to return error code. Why should it be aware of the fact that an error has been generated somewhere very deep and has to be handled a lot higher? So we want a mechanism, in principle, that transfers execution from here, right here. All right. So we would have two mechanisms, actually, checked and unchecked exceptions, as I was saying. Checked exceptions will require recompilation, nevertheless. So checked exceptions are still not what we really want, because this function, which is in the middle, still needs to be aware that an exception would pass through, would have to throws, right, to declare that an exception is being thrown. Even though it doesn't have to do anything explicit other than that. It doesn't have to invent an error code. It doesn't have to modify the code inside its body. All you have to do is add a throws clause to the prototype of the function. Typical implementation is having a try statement and catch finally clauses. Right, and inside the try, you may have a throw statement. In some other languages, this is called raise, and some languages have a slightly different way of handling exceptions. Right, but this is the general idea, right? We enclose a block of code in a try, as a try block, in a try statement, and at the bottom we have a catch. Whatever exception is thrown inside any calls of that body, right? No matter how deep the nesting of calls goes, the catch, the exception handler provided in catch will be a launching pad for the control to come back to. And that's where the exception can be handled. That's where the error condition can be handled, right? So a very typical way is to report the error to the user and ask for, give user a number of options, among which would be retry and cancel. Now, if we don't have function calls, so the difficulty here is having function calls, right? What if the exception is thrown inside a function call? If we don't have function calls, we just have a label break. That's all we have, right? And we have implemented label breaks, and it's nothing more than that. We can provide a dummy while loop that serves as a try statement, and we use a break to jump from all the nestings right outside that dummy while loop. Whenever we have function calls, however, we have to handle non-local returns. So as I was telling you, it may be the case that F calls G, G calls H, H throws the exception, and this guy has to return right back into F, bypassing G altogether, right? So it's a non-local return. We don't return to the place of calling. And we'll see how that can be handled. We're going to look at first at the example, the simplest example, the one that doesn't have function calls. So we have a try block. We have some code here. This may contain some if or while or whatever, right? So it's not guaranteed that this throw will execute every single time. Sometimes it executes, sometimes it doesn't, right? So, and this throw may appear inside other blocks. So I may have a while inside another while, inside an if, inside a for, and somewhere deep inside this block nesting, there may be a throw. Whenever the throw is executed, we want to go from here back to here, and we want this variable to hold all the information that was stored inside this expression. All right? And essentially, the dispatching is performed on type. Actually, this exe may have multiple types because we are already in an object-oriented setting, and we have polymorphism. So there is a base class for this exception, and this exception actually may be a subclass of that base class, right? We're declaring it as a base class, but we may throw any subclass, any sub-object of that class. So the dispatch is based on object. The type of exe is considered, and if the type is this one, then this guy will hold all the information in its expression, and the code that is placed here is executed, right? Otherwise, if the type of the exception is exe2, then this expression will be stored in E, and this code will be executed, right? So the type of the exception is important. If none of the type matches, if it's a third type, it means that the exception has not been caught and handled. Now Java, as opposed to C, has a finally clause, and this clause executes no matter what, irrespective of whether an exception was thrown or what kind of exception was thrown. So if we terminate this throw statement, this try statement normally, if we get to the bottom of the try, we still have to go through finally. If we catch and we find ourselves here, we still have to go through the finally, right? So finally is a clause that executes no matter what, and it's very useful to have this kind of clause, because this will ensure that certain operations that are, for instance, like saving a file or closing a lock, unlocking a lock, right, or deallocating memory or destroying some objects, where you can ensure that this will be performed no matter what, right? We won't leave behind open files or locked locks that might lead to deadlock or something like that. Notice that you might think that placing the code in finally, placing it here would be the same thing, but it's not, because if the exception that is thrown here is of type exe3, for instance, which is not represented here, then neither of these guys would match. This doesn't match, this doesn't match. And then because we are in the middle of handling an exception which cannot be handled in this code, the throw statement will push the execution outside of this block, looking for further places along the stack, in the stack, that could handle the exception. So this code will not be executed either. However, the exception semantics is such that this guy will be executed no matter what. All right. So remember that try statements can be nested. We can have try, and we can have another try here, and we can have a throw, and then we can have a catch here, and then maybe later we can have another catch, right? So this guy, and we're going to have some expression here. So when this throw of an exception is performed, right, if this type matches the type that is expected here, then we use this catch. Otherwise, the exception is rethrown, right there on the spot, right? So the only thing we look at is catch, and the exception should be rethrown, and we end up here, and we try to match it here. If this one doesn't match, we throw it again. However, if we have a finally field here, right, before the exception is rethrown, so now we are in the context of this try block. Before the exception is rethrown, so remember, this exception doesn't match the catch here, all right, and maybe it doesn't match the catch here either, right? So the temptation would be to rethrow and go here, but not before the finally has been executed. So it will go from here through the finally, then maybe here we'll have another finally. So this will execute, and then maybe outside at a shallower nesting level we have another finally. So all the finallys will execute as the exception keeps being propagated in search for a handler that matches its time. So the finally is very important, right? The finally is executed no matter what. This will only execute if the exception has been handled here, or if no exception has been thrown, right? So this is executed right outside the family. Executed if no exception or exception handled. If the exception hasn't been handled by either of these catches, this guy doesn't get executed. Only the finally gets executed. So now we are still in the case when we don't have any function calls, right? So this should be very easy. So let's see a possible translation. The statements are color-coded, so this will correspond to the throw, and this will correspond to the first catch, and this will correspond to the second catch, and finally will go here. So first of all, we want to encode the information that we have in a structure that will so now this is C, right? This is how we would translate the exception handling into C. So we would invent a number of types, one for each kind of exception that we want to throw, and these will be very likely symbolic constants or something like that, right? And one of the types actually will be set to mean no exception. It's the one that you see here, right? So we declare this exception inside this block, and we have this variable E, and initially we set up E to represent no exception because we don't see any exception being thrown. All right, and so this is what happens here. Now we keep executing, and remember, this doesn't mean that it's linear execution. So this throw is not guaranteed to be thrown all the time. Sometimes it is thrown. We go through this code fragment many times. Sometimes the throw is executed, sometimes it isn't. So what do we do when we have to execute this code? What do we do at the C level? Well, we first of all set the type of the exception to reflect the type of this guy. And then E will have several other fields, right? So the other fields will be filled up with whatever other information we have here, right? So this exception may have integer fields, string fields, right? That might explain where the exception originated, and what is the reason for the exception, and so on, right? So right here, right after setting the exception type, we might fill E with more relevant data. And then we jump to catch clauses, which is here, right? So we have an area in the program that handles the exception. It's essentially the translation of all the catch clauses. Obviously, you would wonder, and you're probably right in your assumption, this ... corresponds to this ... right? So this goto is necessary. We have to skip over some code in order to perform the catch. And obviously this ... corresponds to this ... right? There might be some ifs inside here that will make this goto not execute every single time. So we go to these catch clauses, and the first thing we need to do is see whether the type of the exception that is being thrown matches the types that are declared here, either of them, right? So we dispatch on type. So if we have an exception of the first type, then all this code can be copied here. We execute whatever we do there, right? Obviously, there will be a translation because here we will access the information inside E, and that information has to be translated in terms of the members of the structure XC, right? So, but we do here whatever we need to do. And then when we finish, we would like to have a break here. But break is not quite the right thing because we still need to perform the finally. And the finally will appear as the default of the switch case. Right? But we don't want to break out. We still want to execute. After we have finished the handler, executing the handler, we still want to execute the finally, right? So from here we go here to execute the finally. Now, if the type is this one, right, then the code that you see here is executed here, and again, we have handled the exception, but we still have to execute the finally. Now, if no exception has been thrown, it means that we have gone through the entire code here. No exception has been thrown, and we have reached this place, which corresponds to the bottom of the try block here. And from here, we should avoid all the catches, and we should go right inside the finally. Right? So this is what happens here. at this point, if we have gone through the entire code without encountering an exception, then the value of t is still no exception, right? And when we switch here, we're going to jump to this label, okay? And we still execute the finally code, and then we break. This is a very straightforward translation, right? But it is so straightforward because there are no function calls. So let's go further, and we're essentially implementing checked exceptions. This would be the mechanism of implementing checked exceptions. But let's not jump there, right? So how do we handle function calls? The checked exception approach performs the following, is in the following way, right? Each function is instrumented to return a more general type. It returns a structure. So let's say that initially we started with a function f that returns an int. Well, now we're going to embed the int into an exception, into a structure that represents a potential exception, right? So what we have in here is going to be, we're going to have the return value. So sorry, int return value, int return value, and potentially there's an exception, right? So we're going to have an exception type, and we're going to have exception value. So we instrument every function to return something like this. And then, upon return, the immediate thing that we do is check whether this return value, which is now of this type, represents an exception that is being thrown. If it is, right, we have two possibilities. One, the exception may be handled inside f. There is a try-catch block there. If it isn't, it means that we have to pass the exception through f. So we make pass the exception through the current function, which called f. Right? Let's say that was function g, right? G called f. So g, if we'll check the return value of f, because an exception, it simply returns immediately, and the return value of g is also instrumented, and it will reflect the fact that an exception is being thrown. Right? So that's how it works. Actually, in checked exceptions, we do not have non-local returns. We have instrumented returns, and every function is called, then the return value is checked immediately. Right? And if that return value, which is an encapsulation, a more general return type, which contains information about a possible exception being thrown, if that reflects that an exception is being thrown indeed, then either if G has the ability to handle the exception, it jumps to where the exception is being handled. Otherwise, it just returns immediately with its own return value that reflects an exception being thrown. Right? So it's a threading option. But obviously, you can think of it as a non-local return because G essentially does not execute its full body. It doesn't perform a normal return. All right. So if we don't have the possibility of handling the exception, we re-raise or rethrow, whatever you want to call it. All right. So for unchecked exceptions, we're going to see later, the functions do not need to be aware of exceptions, and we have a set of a pair of functions that manipulate the stack and perform a non-local return. They simply wipe out the stack up to the point where the exception can be handled. All right, and we're going to see that in a minute. All right, so let me see. What do we start here with first? We're starting with checked exception. So we're going to have this running example. I already announced that we would. We have function f, right, which calls g. G calls h, and h is this guy. So f can handle an exception of type E1. All right. G does not handle any exceptions. It simply calls h and hopes that h returns normally and would return with its own value, right? And in principle, we want to make assumptions here that fr might be returned. And then we have a function h, which may throw two exceptions, but by no means this is not linear code, right? It may contain ifs in such a way that sometimes no exception is thrown at all, sometimes E1 may be thrown, some other times E2 may be thrown. Now, exception E2 is caught here. And we also have a finally. Exception E1 is only caught here, right? So if we throw E1 here, then we need a non-local return right here. We need to sort of bypass G. So we'll see that we actually, in checked exceptions, we don't bypass G, but G will check the return value of this guy and immediately return, right? Immediately return here. If the exception is thrown, F will check the return value of G and immediately jump here if an exception is being thrown. If the return value of G reflects the fact that an exception is in the process of being thrown. So let's look at the translation step by step. So as I was saying, we're going to declare a global structure that instruments the return value of every function from this point on. And I'm just going to assume that the return values are integers, right? And see that I corrected here. We're assuming that f returns some expression r. So this would be the return value that used to be returned in the C++ version. We're going to call this the C++ version. This is the C version, right? But this structure has several other fields. There's one called exception type, which should be an encoding of either E1, right, or E2. You have seen an E2 being thrown on the previous slide, or no exception. So this would be the field saying that no exception is being thrown. There will be a specific symbolic constant reflecting that for this time. And if an exception is being thrown, of course, normally we would not simply right, we have to set up the exception. The exception has to contain some information. The exception is an object, may contain a string, may contain other stuff, right? So we're going to assume that this field is actually a compound, another structure, right, that contains all that information, and that information is available under the name V. Anything that you put normally in an exception, string, error codes, whatever, would be possible to place inside V. So now, how do we translate F? So obviously, this would be a translation of this, right? The try becomes this start of a block where we get prepared for a possible exception, right? And then this code will be this code, and then we call G. When G returns, G no longer returns an integer. It returns a structure of this form, right? You see that here, the result of G is not used, but nevertheless, it might as well be. We don't mind. So if the result of G is used, then the result of G should be available in this field, right, in the red block. So we call G, we get back this structure. So at this point, we can check whether G is in the process, or as we come back from G, we are in the process of handling an exception. An exception is being thrown, right? So what's the easiest way to do that? We dispatch on the type of the exception. But remember that one possible value of this T is no exception, in which case we would go here directly, right? So depending on the type of T, we might go here, which means that we're handling exception E1, meaning E1 is being thrown, right? Or there may be no exception, in which case we end up here, right? And remember that we always want to execute the finally. So this is the normal thing to do. As we come out of the try, we always want to execute the finally. Right, so dispatch. This is the code that handles the exception, right? And this is the code that handles the finally. All right, so I'm writing the goto here because there might be many cases, so we want a goto finally at the end of each case. This is the finally block, so whatever is here comes from. Oh, I don't have the finally here, but I might as well have. Right. So if there's no finally here, this code is empty. All right, but even so, we still have to put it there, right? We always want to have a finally. We'll see that this is even more important for unchecked exceptions. And we what happens in the case of default? In the case of default, it means that it wasn't T1 and it wasn't no exception. It must be some other exception, in which case we have to rethrow. So whatever we have received from G, we pass on up the stream of calls, right? That's all we can do. So this means that we are in the process of handling an exception, but the exception cannot be handled in the current method. It has to be handled at a higher level. Now, if we have made it to this point, it means that we can safely return our value R. All right, so we have to declare a function that should hold the value, right? And it is very important that we set the type to no exception, right? There's no exception being thrown. This is what will make the caller of f consider R as a return value, right? We'll see this as relevant. If this is different from no exception, then this field will be relevant. The assumption would be that the red val is not set, is redundant, whereas no exception, whereas with no exception, R is redundant, is relevant. So this is returned, and we're out of F. Okay, now the interesting aspect, which is actually to a certain extent not so flexible and not so modular, right? It's not necessarily a good option for modular design, is that in the translation of G, we still have to instrument G. See, G is not concerned with what happens inside H. It may want the return value of H. Let's say we have an RH here that may represent the return value of H. Then it doesn't want to be concerned with the fact that H throws an exception. Nevertheless, G has to be instrumented. Now, if we have the source of G, this is no big deal. We're still happy because all we have to do is recompile G. The compiler will figure out that H might return an exception, might yield an exception, and we'll decide to instrument G as it recompiles. But we won't be able to use G in a readily compiled form, in a compiled library. So let's see, how is G instrumented? In the same way, right? We're essentially returning a structure, and this structure would have a type that reflects whether an exception is being thrown or not. And right, so what we do is we translate into C, and when we reach the point of calling H, we set up this structure that should hold the return value, the instrumented return value, and we use it to collect the return from H. So now H may be throwing an exception or not, right? So how do we know? We check the type, all right? And because we're not handling any exceptions here, the only thing we can do is check whether T is an exception or not, right? If it's different from no exception, then an exception is being thrown. What can we do in that case? We can't handle it, so we can rethrow. That's all. We can take hret, and which is also a struct E, so it's a valid return value for G, and we can return it, and whatever exception is encoded inside here will be made available to F, which can handle some of the exceptions. If no exception has been thrown, if the return value of H is exactly this one, right, and we have made it to this point through execution, we have to return R, but we can't directly return R. Remember, this R should be an integer, right? But here, the return value should be an E, so we have to embed the R inside a structure. So we declare a structure that should serve as a return value. We should set the type of that structure to no exception. We should store inside the structure the variable R, and then we can return that structure. Okay, and the result will be made available to F. Finally, let's see how we would encode H. So, very similar. The try will lead to this block being open, and we declare a structure that should hold the return value of H. Whenever it's time to return H, to return the value of H, right, we should return whatever we have stored in here, right? And we might be returning an exception, or we might be returning a valid value. Whenever we need to throw E1, what we need to do is set the type to E1. So we're assuming this is a symbolic constant that encodes the type of E1, and the value, right, of the exception, the V of the exception, should be set to whatever the contents of E1 is, right? So this should be equivalent to whatever is the contents of E1. And then we can proceed to catch. So now it is interesting because some of the exceptions are handled inside this function inside H, and some of the exceptions are handled in F. Right? So let's see how we can do that. So we are going to catch, and this is very similar to the case when we were looking at the try as a labeled break. Right? So we're going to the catch here. And the same with this exception, right? If we're throwing E2, we have to set the type of HRET to reflect the type of E2. We have to set the value to reflect the contents of E2, and again we can go to catch. Right? So now in catch we dispatch on type as we did previously. The only exception we can handle inside here is E2, right? So we will have a case E2. And whatever code we have here, we place a translation here, and at the end of the translation we have handled the exception. So we can change the type of T to no exception, and we can go to finally. Right? Inside finally, we perform whatever is supposed to be performed inside of finally, and then we check, has the exception been handled? If we have come from handling it here, right, if we have come from here, right, then the type will be equal to no exception. So we can go to break, come out, right, and return HRET, right? We are setting the return value to be the R, the expression R that we would normally return, and we return HRET as a valid return value. Okay? So if the exception that was thrown was E2, which can be handled here, we would have signaled through this assignment that the exception has been handled, right? So there's no need to rethrow. There's no need to rethrow. This will rethrow the exception. Now, if the exception that was thrown was E1, we're going to go inside the switch. We're going to check the type, right? The type is E1. So the only case that we have here is E2. So on E1, we would go to default, right? And what happens inside default? Well, we still have to execute the finally. So default and finally are actually placed in the same place. This time, however, we would not have this. This will be true, right? So we're coming from E2. We haven't executed anything. We go through finally, and when we reach the end, we find out that the exception has not been handled yet. There's no piece of code that would assign T to no exception. So this will be true, right? T is still E2. This is still E1. So it's not equal to no exception. So in which case we rethrow. So whatever is encoded inside HRET, which is an exception of type E1, is passed on to the upper level, which is G. And remember, G will just notice that HRET is different from no exception, and we'll pass it on to F, which F can handle the exception of type U. So this would be, in essence, the translation. It's an instrumented translation where the return value encodes whether an exception is currently being thrown, right? And if it's not, it will just store the regular result that the function would otherwise return. So this is all about checked exceptions. So if you have any questions, of course, feel free to ask in the forum or contact me on Google Talk. This is where in a normal lecture I would stop and wait for questions, but obviously it can be done in offline recording. The next topic that we want to talk is checked exceptions, unchecked exceptions. And in order to understand the implementation of those, we have to learn, or maybe revise, remember, two very interesting functions in the C standard library: set jump and long jump. Set jump performs a save, saves the state of the current stack and the register values of the processor in such a way that, so remember that as we go through a sequence of nested procedures, right? We go through a sequence of call. F calls G, G calls H, H calls P, and so on, right? We have activation records created on the stack, right? And then the normal returns will use the activation records to return back to the places of calls, right? But these functions will allow us to perform a long jump. We could return from the innermost caller directly to the outermost caller, completely bypassing these two functions, which is a behavior similar to what happens in exceptions. So how do we do that? Well, set jump will save this state of the stack, right, corresponding to this, to the execution of the outermost function. Then, inside here, this guy calls a long jump, which restores this state. So suddenly, all these activation records are removed, and the program finds itself forced to execute from the saved state, and it will just go back inside the function where the state was saved. Okay, so to understand exactly how this works, let's look at an example. Right, you have a summary here, but there are plenty of examples on the web. If you look for set jump, long jump examples, you will get many. And I'm giving you here the example that appears in the Wikipedia page of for set jump, long jump. So let's consider a sequence of calls. So we have main, which calls first, which in turn calls second. Sorry for this. This is part of the command. So this would be a one-line command, and it's not really executable code, right? So what do we do here? Well, you see, we perform this set jump inside an if test. Set jump saves the state of the stack in this storage space called buff. You see it declared here as a global variable. It has to be global because we want to access from other functions. You will see it accessed from here, and it has to be global so as to be shared. And if this is the call to set jump, it always returns 0. All right? So the value returned is 0, and because we're negating, this will evaluate the true in the first call. In the first call, in the call to set jump, it will always evaluate the true. So we go and call first calls second, right? And we would expect what? That, as first gets executed, it calls second. We return from the call to second, and then we get to print this guy. Okay? And also, if we go back to main, since this guy always returns 0, set jump returns 0, this is always true, this we would expect to not be executed. Okay? But we'll see exactly the opposite. We'll see that this one doesn't get executed, and this one does get executed. So remember, first we go here, call second. In second, we perform this print to just remember where we are, and then we perform a long jump with a value of 1 here. So long jump does what? Restores whatever was saved here. So after, while inside the long jump, this is restored. So execution jumps right here at the end of set jump. So you execute long jump, and suddenly you find yourself as if you have just returned from set jump. As if you have just returned from set jump. But the return value from set jump is now 1. So it's a very interesting thing, right? First time when you call set jump, it saves this buffer and it returns 0. Right? When you call long jump, right, it places the program in a state so that the program sort of believes that it has just returned from set jump, and the return value from set jump is whatever we have given here. So at this time we have a 1. This guy becomes false. We jump here, and we're going to print the statement in main. All right, so we're simulating a second return from set jump with a return value of 1. So we're going to go here. All right. So notice what happened. Right from here we have from here we have jumped here essentially, and this is something that we could use to simulate exceptions. Right. We have completely bypassed this guy, and this guy noticed that it doesn't need to be aware in any way that an exception might be thrown. So when implementing unchecked exceptions, we won't instrument anymore. The return types of our functions will stay the same, right? We're just going to have a scheme for translating try-catch blocks into if blocks, where we would use set jump and long jump. So we're going to use the same 3 functions, f, g, h, right? And we're going to see how the translation proceeds this time. So now, because we can have nested try blocks, we're going to need to implement a stack of buffers. Right? So this jump buffer is a storage area that can hold the state of a procedure call. Right? And we need a stack of them. Now, to operate on this stack, we're going to have 2 functions, push and pop. But these functions do not operate as you might be used to when it comes to a stack and push and pop, right? Usually we push and take an argument, right? So we push and we expect some argument to be given here, which is pushed on the stack. And when we pop, right, we expect some return value. No such thing here. When we push, right? When we push, so let's see how these 2 functions work. When we push, we add a record on the stack, and we return its address. So the return value of the push is the address, and you see that push is going to be used here in set jump, all right? And that's great because we have added an empty record, all right? We return the address, which is the perfect argument for set jump, which can fill this thing with a state. So we don't really need to take an argument for push. It is sufficient to just create an empty record. When we do pop, what we want to do is move the stack pointer to the previous record so as to shrink the stack, but return the old top of the stack, the address of the old top of the stack, right? This is used here. So what we need to do is, yes, shrink the stack, but where do we need to jump? We need to jump to the state that was recorded here. All right, so pop decreases the stack pointer, but returns the address of the record of the buffer at the old stack pointer of the address of the buffer that has just been removed. So then we can perform, use it for long jump. So they will be used here, right? So when we set jump, we want to save it into a new record on the stack. When we perform the long jump, when we jump back, we want to remove that record so that if we have nested try catch blocks, all of them get a chance to be considered, right, as we traverse the stack. Notice that what's going to happen is G doesn't need to be aware that any exception is being thrown. So that's really good news. It's a lot more modular in this respect. So G remains the same. Not the same as in the initial C version of a function that returns int and just calls h inside. So let's see how we translate f. All right. So obviously this try is going to become this if statement. G, so calls remain unchanged, right? Essentially. But what we do in try is we save the state, right? We create a new record and we save the state. We call G. G we'll call h, which might throw an exception. And if that happens, the throw will be a long jump, and the long jump, as you remember, will take us right here, right? Which is where the catch is being translated, right? So that's the perfect behavior, exactly the behavior that we need. So let's see how this works, right? So G is called. If no exception is being thrown, we have made it up to this point. It means that the state that we have saved is not needed anymore. So we perform a pop to just discard the record, the buffer on the stack that was added by this push. All right, there's no need for it anymore. Otherwise, if we have encountered an exception, right, the long jump will be performed when that exception is thrown, and we're going to jump right here. And again, we're going to have a global, or maybe this time, previous time we didn't have a global exception data structure. Now we're going to have a global exception variable, right, that holds the currently thrown exception. So this exception will be set by whoever is throwing the exception to have a type that reflects the type of exception being thrown. So we have to dispatch on type again, and if it is E1, which is the only exception type that we can handle here, then all this code goes in here, and at the end, as we did before, it means that we have handled the exception, so we have to signal that by this assignment, right? And again, we have to execute the finally code. So we just go to finally. If no exception is being thrown, all right, if no exception is being thrown, okay, there might be a problem here because I have forgotten to put a go to finally here. All right, so go to finally should be right after pop, because we still want to execute the finally code. So as we find ourselves at the finally code, we don't have a finally here, but we might as well have. So if we have, then whatever code comes here will go here, but this may be empty. And here we have to check whether the exception has been handled. And if it hasn't been handled, we have to rethrow it. Right? And where do we go? Well, to the outer try catch block, right? Which should be at the top of the stack. We rethrow this. So this is the rethrow. However, if this exception type is equal to no exception, which means that we have just come from here, or we have come from here, we have reached the bottom without an exception being thrown. We have reached the bottom of the try block. Then this if statement is false. So we just come out of the try catch block, or the translation of the try catch block, if you will, and we can now return the usual result R. And notice that we do not have to change the type of F. It remains the same. All right, so we have changed a little bit the code. The try and catch have become if statements, but most of the code can be reused, and there's no need to change the types. G remains the same. All right, and let's see how we translate H. So same scheme. Try becomes an if. All right, And again, we call set jump, and we push. Sorry for this. Push should have brackets to show that it's a function call. So we call push, and we create a record on the stack where we save the current state of the stack, and this goes here. Then if we want to throw E1 at some point, we have to set up E1. So the type of the global variable exception will be set to this type, and the contents will be set here, and then we perform a long jump with a pop, right? If the exception that we want to throw is E2, then we set a type, and we set a contents, and we do a long jump of a pop. If we have made it to this point, it means that no exception is being thrown, and we can just pop the element from the stack. And here we also need to have a go to finally. Okay? Or alternatively, we could take all the finally here. We can take it and put it outside. All right. So same as the previous case, we dispatch on T. Here we can handle E2, right? If we have handled E2, like if the code here has handled E2, we have to signal that by changing the type to no exception. There's no more exception being thrown, right? We go to finally, and whatever is here is executed. And at the end of finally, we have to check whether we need to rethrow or not, right? So if we have handled the exception, or if no exception was thrown at all, this test is going to be false, right? Which means that from here we can make it out and return our true value. Otherwise, this test is going to be true, so we have to rethrow the exception. Long jump hop will rethrow the exception. Means that we have thrown the exception first, but no, we have taken the default, right? The type of the current exception is neither of the ones that can be handled here. So the only thing is to take the default and rethrow the exception. So this is essentially the implementation of unchecked exceptions. The great advantage is that the functions that do not handle exceptions or do not throw exceptions don't need to be aware of that. They can be placed inside without any worry, and you can actually even compile them and use them in compiled form. There's no need to recompile at the point when you decide, for instance, that H should throw a new exception, or H should throw an exception at all, and F should handle that exception. G is completely oblivious to that. All right. Checked exceptions are, in essence, easier to optimize and more compositional, right? That's because the compiler is forced to look at all the functions, F, G, H, which is something that a Java compiler does do, right? Java compilation is not as modular as the C compilation. In the C compilation, you can compile each file individually without paying any regard to all the other files that may be part of the complete program. Whereas in Java, what happens is that if a method from class 1 calls a method from class 2, the compiler needs to see the source file of class 2 in order to decide whether the call is valid, right? If that class is not available, the compiler would yield an error and would refuse to produce an executable. Right? It's also more amenable to debugging because it doesn't directly manipulate the stack. It allows the normal flow of control of functions. And on the other hand, from a software development perspective, is less flexible. Right? So it's not so easy on the programmer to work with checked exceptions, because whenever they have this middle function that doesn't want to have anything to do with exceptions, but has to let an exception pass through, it has to be declared as it has to have the clause of that declares that an exception is being thrown. For unchecked exceptions, they're a lot more flexible. All right, all this intermediate chain of functions doesn't need to be changed or doesn't need to be aware of the fact that an exception might be thrown, but it has um, it performs stack manipulation, which may throw off a debugger. So if you look at G++, which I did yesterday, the amount of instrumentation that is performed in order to allow the debugger to be aware of exceptions being thrown is tremendous. So in essence, is less amenable to debugging. And it's more difficult to optimize because it becomes an inter-procedural issue, right? So C compilers can do very well, can optimize very well intra-procedural issues. So it's always easier to optimize when you have all the code available, right? But C compilers are not allowed to do that, are not allowed to have that luxury, right? You just compile one file, and it can only make some assumptions about the functions that reside in other files, right? Based on their prototype that is declared in the current file. So since there is no information, full information of right. So it might be the case that you're throwing an exception from a function in one file, and it lands in a function in a different file. So the compiler can make no assumptions about that. It can only follow to the letter the translation scheme that was given for exception. So there's very little opportunity for optimization. All right, so this was our discussion about exceptions. The next topic is that of object-oriented languages. And we want to understand here how polymorphism and inheritance can be implemented. The other important principles of object-oriented languages are encapsulation and data hiding, right? The ability to enforce that certain pieces of data are not accessible, which from a software engineering point of view is important, right? It deals with the aspect of separation of concerns. It enforces modularity. It enforces abstraction. Many projects fall apart because in a moment of weakness, a programmer gives in to the temptation of breaking these rules, right? You might think that, for instance, it's no big deal to write in C because if we decide that there's an abstraction barrier, everybody would understand and respect that. You would be surprised how many, in a large project with maybe hundreds of programmers, how many people would feel tempted to access some piece of data that is not part of the interface, that is part of the implementation, would expose implementation details in a moment of weakness just to finish something quicker, and saying potentially that they will probably change it later, and they never do. And years later, a bug pops up or a bad design pops up and increases the costs of implementing some new feature or whatever, right? So, but these are features that can be implemented at the compiler level, at the semantic analysis level, via static checking, typing, and so on. And another interesting feature that contributes to that is name mangling, which is something that you can see in C++. It's very easy to translate into assembly language and see the names of the functions that the translations of the names of the functions that will be made available at the assembly language level. They very remotely resemble the original names, and they're made in such a way that you cannot easily guess in an object file the name of a data component, for instance. But we want inheritance and polymorphism, right? So let's see how that would. So this is what I just said about encapsulation and data hiding. They're important. Another issue that we need to deal with is scoping. There are several new scopes in an object-oriented language. There's a global scope, there's a class scope. Global scope was there all the time, right? And what do we do with the variables, with objects that we want to create in a global scope? Typically, we allocate them in the heap. With C++, however, it's also possible to allocate them statically. But Java doesn't do that. Java places everything in the heap with the class scope. So we have objects that are statically declared inside the class scope. These will typically be created on the heap. There's an object scope, which is essentially similar to a structure. So whenever we implement objects in, we want to simulate objects in C, we would do that via structures. And then method is similar to function, so the method scope should be implemented on the stack. There's local scope, right? The one that is created by opening a curly brace, so that is also in the stack. And obviously, as with C, there's no difference there. We have to stack up the frames in correct order. So we're going to have activation records for every method. In order to have a polymorphism, we saw that there are many forms of polymorphism. And one thing that we have to handle is the fact that that we may have methods with the same name, but different combination of argument types. So we can have a function f that takes a character as an argument, and we can have another function f that takes an integer as an argument. And we may have yet another function f that may take two integers as arguments. All right. So how does this translate into the C level? Well, we use name mangling, and actually what I'm doing here is just a something that appears reasonable, because if you actually look in the assembly language file generated, you'll see something more complicated. But every function will be translated into every method, right? F is a method of class 1, which takes character as an argument, and will be translated in something like that, right? So the class name becomes part of the name of the function. The original function name, method name, becomes part of the name of the function, and some encoding of the argument types become part of the name of the function, right? So here we're essentially saying that this one returns an integer and takes a car as an argument, right? So we would have some combination of letters indicating the return and the argument types. Necessarily, we need at the C level, we need to ensure that all the names are unique, right? No name clashes should be possible, and this is not always very easy to enforce. Now, let's see how inheritance works and polymorphism. We are interested now in the other kind of polymorphism, where a class extends another class, which may extend another class, right? And we want to find out how, through the concept of dynamic linking, we can isolate the method that needs to be called for each of the objects, right? So we can have some object, and we call method m, right? And this object, right, it belongs to class C1, which extends class C2, which extends class C3 maybe. So where should this method m come from when it is called, right? And actually, that we might have an object C4 that extends class C1. So this is this kind, but sometimes the m that we want to call appears here. And this is what we're going to see in the example today. Because you're always saying that, well, first I write C3, then I write C2, then I write C1, right? C3 is the base class. This is a subclass of C3. This is a subclass of C2. This is a subclass of C1. And well, when I call M either resides in C1 or is inherited from C2 or is inherited from C3. Well, you'll see that actually we might be calling the M that appears here, right? So this is a Java example. Let's see how this works. Let's satisfy ourselves with the fact that we might actually call, you see, when we're going to call this, we're going to wonder which say are we calling. Are we calling this guy or are we calling this guy, right? Seems a bit difficult to believe that this guy might be called. So I'm inside the lecturer, I'm calling say, and it seems a bit difficult to believe that I might be calling this method, but that's what happens in this example. So we have a speaker, and the speaker can just say things, right? So there's a string called an argument called message, and it's just printed, right? So if the speaker says, we ask the speaker to say the sky is blue, what the speaker will do is just print out the sky is blue, right? If then we define a lecturer that extends the speaker, right? So because of this extension, the lecturer inherits the method called say, and we define a new method called lecture, which the lecturer is capable of lecturing, right? Takes a message, and this is how he lectures. He says the message, and then he says that you should be taking notes, right? It's like an old-fashioned lecturer, which who wants to remind the students that they should be taking notes, right? Maybe he's teaching on the whiteboard, right? Drawing diagrams and formulas, and every time he writes something important, he tells his students that they should be taking notes. And then we define an arrogant lecturer. Right. So to go through the example that we have there, whenever we say lecturer.lecture and the sky is blue, whenever MSG is the sky is blue, the lecturer says the sky is blue, and on the next line you should be taking notes. And then we have an arrogant lecturer which extends the lecturer. So because this guy is arrogant, he says things in a different way. All right. So he relies on the say method inherited from the superclass from here. So remember from the lecturer. Remember the lecturer actually doesn't have his own or its own say method, but inherits one from the speaker. So whenever we say super say, we're calling this guy, right? And the arrogant lecturer prepends, it is obvious that, to everything he says. Right? So let's say we have a new arrogant lecturer, and we ask the arrogant lecturer to lecture the sky is blue. All right, so it may come as a surprise, but the response here, the reaction of the arrogant lecturer is going to be, it is obvious that the sky is blue, and it is obvious that you should be taking notes. Right? So what happens is the following. The arrogant lecturer has a lecture method, right? So this one is called. And the lecture method called say. And the question is now, what say method is it called? Right? So many would have a knee-jerk reaction and say that the method would belong to the superclass. It's not here, so it has to be in the superclass. Actually, that's wrong. Actually, that's wrong, because this guy overrides the same method. So as long as we're not qualifying the same method with a class, like here is qualified, right? But here is not qualified, right? So we're coming from here. We're calling the lecturer called say, and we have to go to the overriding. And then inside say, we're selecting this method which belongs to the super, so this will go here, right? And we're going to have that, right? And when we do this say, the same thing will happen. We'll go here, and this guy will call this the qualified say, which goes here, right? So we're taking the message, right? We're taking the message. We're prepending to the message. It is obvious that, and we're going to get, it is obvious that the sky is blue. And then we're going to say this thing. So we go here, we're going to prepend that, it is obvious that, so it is obvious that, and we're using this message. You should be taking notes. So this is what comes out. So how would we implement this? So the C equivalent. Obviously, an object has to be structured. There's no other way. Now, in order to be able to manipulate the functions in the way we did, in order to be able to implement dynamic linking, we have to store inside the object pointers to all its methods, right? So the same method essentially appears inside the object. We can't put an entire piece of code inside a structure, but what we can put is a pointer to that function. So we can define a function, right, that performs the task that was the same task as the corresponding Java method, and we put the we're going to put the pointer to that in here, right? So this is what is going to happen, right? We're going to have an initialization, and obviously, normally we would put here all the data and pointer to methods that an object would normally have, but in our very simple case, we only have one member, which is a pointer to a function, so we keep that. We need a constructor, and we're actually going to split a constructor into two parts, and we'll see how that is useful when we have inheritance. So we call this the constructor, make speaker, and we allocate memory for it, right? And then we call a separate method for initialization, right? So we don't perform the initialization directly here, but we encode it as a separate function. We'll see why this is useful in a minute. And then we return the pointer to the object we have just created. So essentially, if we create a speaker, right, how we can do that, we can say struct speaker p star p equals make speaker. And then we can call the method inside p. So we can say p say. And now you would be tempted to put a string here, but if you look carefully, actually we have added one argument. We always, inside every method, we add as the first argument the pointer to self. This is the equivalent of the keyword this in Java and C++, right? This, if you remember, it is said in all Java and C++ books, right? As you go inside an instance method, you would have this keyword which represents a pointer to or reference to the current object, and is passed as an argument, but that argument doesn't need to be visible inside the declaration of the method, right? However, in C, we have to make this explicit. We have to make this explicit. So we would put here a P, and we will put here a message. So always we have to respect this pattern. P arrow method P, right? P arrow method P arguments. If you forget about this P, then the whole thing doesn't work anymore. You'll see how this is important in a minute. So let's move on to the lecture. The trick that we're going to employ here is the following. We're going to declare the lecturer in such a way that the older speaker is a prefix of the lecturer, and the definition of C guarantees that the fields of a structure will be stored in the same order, meaning that now if I take this lecturer and I turn it into a pointer to a lecturer, I convert it into a pointer to a speaker, right? So I have a speaker and I make it I have a lecturer, and I make it into a speaker star lecturer. So this is a pointer, right? And I say, right? I still get, this is a lecturer, I still get the same method. Why? Because this say field is the first, and in the speaker structure, the say field appears the first as well, right? So the fields that appear in the same order and have the same sizes will be stored at the same offset. Notice again that we have to have the self argument and we have to have the method argument. This is the equivalent of the lecturer lecture, and you might be tempted to say here speaker arrow say or something, right? No, what you have to do is use the self. So the self is a structure to something like this. So from here we can select the say method. So without the self, we would not be able to take advantage of the same method. Now, how are we going to initialize this? Well, we're going to invoke the constructor for the superclass. So this is going to be the maker, the constructor of our class. We perform the allocation, and we call the init lecturer as we did before. But notice that inside the init lecturer, there's another call that initializes the speaker part of the lecture, right? And we can put P here without any worry, because this will only initialize the say part, and the offset of the say inside the speaker and the offset of the say inside the lecture are the same, so there's no danger. And once the say field is initialized, then the lecture field can be initialized right here. Okay, so we always take advantage of the constructors of the superclass. We do not initialize those. And now let's see how overriding is performed. So overriding is performed in the following way. We will still have a say field. We will still have a lecture field, because these are inherited from the speaker and lecturer, but we're going to be overriding. So what we're going to be doing in the lecture is we're going to save the old value in here, and we're going to set this to a new value, right? Now, the arrogant lecturer is going to have its own say method, where it prepends this, it resolves that. And I did that in the C way. I used string concatenation, and right, this is how it worked. And notice how I call the superclass. I will call the super method from the place where it was saved. I'm assuming that that is already done. That will be done by the constructor, by the way. So this is the constructor, and it allocates memory, calls the initialization function. Inside the initialization function, we initialize the lecturer, which will initialize the first two fields, right? The say and the lecture. So this is set to be the say of the speaker. This is set to be the lecturer method of the lecturer. So what do we do now? What do we do now? Here, we're going to save this guy here, and we're going to set this guy to the new value. So whenever anybody is going to call P arrow say, right, it will call, even the lecturer from inside the lecture method, when it's going to call the P arrow say, because this field has been changed, it will call the say of the arrogant lecturer, not the say of the lecturer. Every access to super.say will be translated in this way, and we'll call this method, whose pointer is here, which points to the old say method of the speaker. So everything is fine, right? So notice the fact that this this self is extremely useful in order to perform dynamic linking, right? If I have an arrogant lecturer and I invoke a method that belongs to one of the superclasses, for instance, the lecture method, right? That lecture method, when it calls say, so that lecture method, right? This one, when it calls lecture, when it calls say here, right? This self is the self that was set up by an arrogant lecturer. All right? So when we do self.say, this is the say of an arrogant lecturer. It's not the say of the speaker. All right? And this is how dynamic binding is implemented. Okay, so hopefully this clears up the mechanism of inheritance. And the mechanism of polymorphism was implemented by the fact that we have chosen the structures to be prefixes of each other, right? So this is the speaker, this is the lecturer, this is the arrogant lecturer. And we are very careful to declare the method fields so that they would be at the same offsets, right? So say is at offset 0 everywhere, lecture is at offset 0 everywhere, and this is an extra field that will not be accessible from the speaker and the lecturer, so it doesn't really matter. So we can always view an arrogant lecturer as either a lecturer or a speaker, right? Because if we convert a pointer to an arrogant lecturer into a pointer to a lecturer, the pointer to a lecturer will see only these two fields, right, which are compatible with the lecturer. There's a say and there's a lecture field, right? And then if the lecturer gets converted to a speaker, they're also compatible, right? These parts are compatible. When the lecturer is converted into a speaker, only the first field of the lecturer is visible, which is compatible with the speaker. So this is what the main function would look like, right? So we create a lecturer, an arrogant lecturer, and then remember this pattern: P arrow lecture P. This seems redundant. It's not at all redundant, right? If you forget about the P there, everything is nothing works anymore. So remember, as a summary, each class is compiled into a structure. Data members remain the same, right? Everything, we didn't have any data members here, but they would remain the same. And we have to convert the methods in such a way that pointers to methods are stored inside the object. Each method would be compiled in a function with a mangled name. We have our own mangling. The first argument has to be a pointer to self, and we always call it into via the corresponding point. Polymorphism is realized by arranging the structures so that each of them is a prefix of the next. And by the way, this allows a class to extend only one other class, right? So if we want to allow the style of C++ where a class may extend several classes, that would require more work. Constructors are split into two parts, one that performs allocation and one that performs initialization. The initialization will call the initializer of the superclass. That's very important, right? You don't want to initialize those fields yourself. You want, because if you go and change the superclass, then you want to not go everywhere and make changes across all the subclasses to reflect the changes that you made in the superclass. Methods have this pattern. It's very important to remember that. So, because of that, we have polymorphism, right? The way we perform class extension, I just said that. And remember, when we overload, so the method M of the arrogant lecturer overrides, not overload. Sorry, override. When the method of the same method of the arrogant lecturer overrides the same method of the speaker. So the overridden method has to be saved so that they may still be called if needed. All right. There are a number of optimizations that we can do. In fact, we don't have to have pointers to methods inside every object, because that's a bit of a waste, because those pointers are always the same, always have the same values. So it's a replication of the same data, so that's redundant. What we can do is have a class-wide table that contains all the pointers to all the methods of every object. and we can access the pointers through that table. All right, so this is pretty much it. If you have any questions, use the forum or catch me on Google Talk. I will see you next time in class.